Hi, pre-cal friends, and welcome to week 1 of remote learning. Our objective today is we are going to operate with vectors in 2 dimensions to model and solve problems. I know that sounds super exciting. Our agenda for today, I'm going to give you some information about the Chapter 5 test, which is what we would have taken the week that school closed. Our new material today, you've probably figured out based on our objective, is the vectors. Your quote homework will be completing the Unit 14 test from the AFM course in GradPoint, and you will have some practice problems from 6.1 and 6.2 out of your textbook. My office hours are going to be Monday through Friday from 1 to 2. During that time, you can reach me by email, and if I need to set up a Google Meet, I can. But please feel free to email me at any time. Just know that immediate responses will not be guaranteed if your email is outside of office hours. All right, here we go. Information about the test. So some of you had already been added to GradPoint because you were doing some extra credit work. But even if you have not done that, you have now all been added. And the way that you access GradPoint is through the Millbrook homepage. You'll click on the Students tab, and then there's a link for GradPoint, and then your login and your password are both your student ID number. To take the place of what would have been our paper pencil test for Chapter 5, you're going to be taking the post-test for Unit 14. There are quizzes also in Unit 14. Those are optional. You can use those to help you review and prepare. The only thing with those will not count for a grade unless you did not take the 5.1 to 5.4 quiz before school was dismissed. If you miss that quiz, then quiz number 1 will be used as your grade. I think at least one person has made that up, and by the time you're watching this video, hopefully some more of you have done that one as well. If you have any problems accessing GradPoint, shoot me an email and I'll see what we can figure out. All right, so Chapter 6 in our book is called Vectors, Parametric Equations, and Polar Equations. Again, this week we're going to study vectors, parametric. I'm kind of not really sure how much we're going to be able to do with parametric since not everyone has a graphing calculator at home. Desmos works okay, but it's not great based on what I've seen for the applications that I wanted to do with you, but we will definitely do polar equations. So today we're going to cover section 6.1 and 6.2 from your textbook. I'm definitely not doing as much as I would have in the classroom, but doing the best we can with remote learning. But 6.1 is called Vectors in the Plane, and it's found on pages 502 through 510. All right, so start us off with a multiple choice question. What is the name of the figure pictured below? Is it letter A, segment PQ, letter B, line PQ, letter C, ray PQ, letter D, vector PQ, or letter E, both C and D? All right, drum roll. The correct answer is E. This shape, symbol, whatever you want to call it, can be considered a ray as well as a vector. So in geometry, the definition of a ray is a portion of a line that starts at a point and goes in a particular direction to infinity. So it doesn't stop. So you may remember that from studying when you study geometry. In pre-calculus, we call this a vector and is a directed line. So it's going in a direction. So a directed line segment with an initial point, so initial, think starting, and a terminal point, so think about terminate, something's ending, that has length, which typically we use the word magnitude to represent length. So if I just showed you a picture, you don't really know if it's a ray or a vector, but since we are studying pre-calculus, we will be talking about vectors. So I'll give you a minute if you want to jot down the definition for vector. You don't need the definition of array. That was just a little bit of review for you. I'm going to move on to the next slide. Obviously, I can't see your faces if you need more time, so you may need to pause the video throughout. You guys can give me some feedback via email as far as pacing and how this goes. All right, so here we have that same picture. And again, we've decided this is called vector PQ. Notice the P is listed first and the Q is second. That is because the P is where it starts. So our initial point is going to be point P. Our terminal point, even though it looks like it keeps going on forever, the arrow is really just showing you the direction. So the terminal point is Q. And the length or the magnitude, how long this vector is, it's represented with absolute value bars. And so we can put PQ in here, vector PQ. And so we think about absolute value, meaning it's positive, and the definition of absolute value is the distance from 0, which is your length, how long something is. So anytime you see a vector inside absolute value bars, it's asking you for the magnitude or the length of that vector. All right, so vectors can be written in component form. It kind of looks like an ordered pair, except that we do not use parentheses. I call these alligator brackets, totally a Ms. Yop thing. Definitely not really mathematical, but it works for me. So it says a vector can be represented as an ordered pair. We think of it as x comma y when we do ordered pairs. And if you think about your x-axis is your horizontal axis and your y-axis is your vertical axis. So these two numbers represent the horizontal component of a vector and the vertical component of a vector. I know that doesn't make much sense now, but hang tight. I promise I will do my best to explain it using my amazing drawing skills. I didn't mention it earlier. Hopefully you guys have got paper in front of you. The other thing that might be helpful if you have some graph paper, otherwise you can just sketch it. I don't really think you're going to need a calculator, at least for the first part of this lesson. For lesson 2, you probably will need your calculator. And again, you can use Desmos if you do not have a graphing calculator at home with you. A couple of you had reached out to me about graphing calculators, and the school is not distributing those, so you will just need to use, if you don't have your own, use Desmos, or you can hopefully download a free calculator, possibly on your phone, tablet, or computer. Okay, moving on. So this is find the component form and the magnitude of vector PQ, where P is the point -3, 4, and Q is the point 1, 2. So we're going to start off plotting the initial point, which would be P. So -3, 4. Let's get my pen turned on. So there's the initial point. And then the terminal point, so where the vector is going to end, is 1, 2. Then when we draw the vector in, we do use an arrow because that shows me which of the 2 points is the terminal point. We talked about the component form being the horizontal and vertical components. So as we start to work through this, we need to figure out, how do I get from point P to point Q? And since we said that in that component form, it is horizontal, comma, vertical inside of our alligator brackets. If we think about how do we get from P to Q? Well, horizontally, I'm going to go to the right, and if we count that, that's 1, 2, 3, 4 units. And to the right is positive, so that would be 4. And then my vertical component, I am going down, and since down is in a negative direction, that would be a -2. So this vector with initial point -3, 4 and terminal point 1, 2 can be written in component form, and it is 4, -2. You might have noticed that as I drew in those horizontal and vertical components, we made one of our favorites, the right triangle. So it's very easy now, since we did this graphically, to calculate the magnitude of the vector. And because it's a right triangle, we can use our favorite, the Pythagorean Theorem. So again, many of you like a squared plus b squared equals c squared. You guys know I prefer leg squared plus leg squared equals hypotenuse squared. Sorry about the extra line there. So it doesn't matter which one's which. So we've got 4 squared plus -2 squared equals my hypotenuse squared. 4 squared is going to give us 16. -2 squared is going to give us 4. Please be careful, don't tell me -4, as you guys tend to do. And that is 20. But that's the hypotenuse squared. So to find the actual hypotenuse, we take the square root. And so the magnitude of my vector is the square root of 20. Keep in mind that as you do practice problems in the textbook and you're checking your answers in the back, my guess is they will probably simplify those radicals. But again, I'm fine with you leaving them just as the square root of 20. Again, no need to pick up a calculator to do a decimal approximation. So to me, that's the easiest way to find the component form and the magnitude of a vector. It's just by drawing, and then we don't have to memorize any formulas. If you look in your book, they're going to go in much more detail and do a more of a formula-oriented approach. I think they have this one as well. But again, because this is remote learning and I don't have you guys in front of me, I'm trying to pick the easiest possible way to present this to you. So I changed one here. One of these vectors, it was going to go off the page for a later graph. So it gives you two vectors, and again, we know they're vectors because of the alligator brackets and not parentheses. Again, parentheses are ordered pairs, so that would be a point. So vector u is -1, 3, and vector v is 4, 2, and it asks us to find the component form of these vectors. In your textbook, it goes through a lot of instruction and like all these scary looking formulas of how to do this, but I think this is pretty self-explanatory, and you guys are very bright. I think it will pick up on this very easily. Because we kind of treat them like ordered pairs, even though they're not ordered pairs, when it says u plus v, you're going to add the x coordinates, aka your horizontal components, and then add your vertical components, which are your y coordinates. So for u plus v, I'm going to have -1 plus 4, because those are my horizontal components, and then 3 plus 2, which would be my vertical components. So I'm showing my work here on this first one. So -1 plus 4, 3, 3 plus 2, 5. And if I make a mistake, sorry, I don't have you guys in front of me to correct me. Feel free to email me. Letter B has 3u, so that just means 3 times u, so it's going to be 3 times as long. So we just put a 3 out in front of vector u, so -1, 3. And then it's really just like the distributive property. So we're going to distribute that 3 to both the horizontal and vertical components. So this vector would be -3, 9. And then lastly, this one's kind of a two-step. So we have 2 times vector u. And again, notice I'm trying to be careful and make sure I'm using my alligator brackets. Vector u was -1, 3. Minus vector v, which is 4, 2. And so then we can distribute -2, 6 minus 4, 2. So if we take -2 minus 4, that gives us -6, and then 6 minus 2 would give us 4. So those are some operations, again, I think pretty easy to follow. It kind of is, I think, they kind of work the way you think they would. So, you know me, I like for you guys to understand where this is coming from. So I want you to look, well, I only do one of these, I think that's all I prepared, was to look at u plus v graphically. Obviously, it's very easy to add them algebraically, as we did on the previous slide, but like, what is it actually doing in terms of a vector? So again, I'm using those same two vectors, and that's why I changed this one, because my graph paper wasn't large enough with the original numbers I had chosen. So first thing I'm going to do is draw in vector u. So vector u says -1, 3. And I don't think I mentioned this earlier, but our vectors, typically we start in standard position, which means they're going to start at the origin. So I'm going to start here at 0, 0 would be my initial point. And then -1, so I go to the left one, up 3. And so this would be vector, and I'm going to label that u. So that's my vector u. Then I'm going to add on to that vector v. And vector v is 4, 2. And instead of going back to the origin, again, I'm trying to add that vector onto vector u. So I'm going to start at my terminal point of my previous vector. So at -1, 3, from that point, I'm going to go to the right 4 units and then up 2 units, because that still represents the vector 4, 2. So there's vector v. And so now we need to find their sum. And so if I connect my initial point, which was the origin, to the terminal point after I added them together, this gives me the vector u plus v. And if you notice, that vector, if we look at the terminal point based on the origin, we go to the right 3, which is a +3, and up 5. And if we go back to the previous slide, I think that we will see that we get the same answer. So I just, you know me, I think it's important for you guys to understand both graphically and algebraically. All right, moving on. You guys, I know one of your favorite things is our unit circle, and just a reminder, the reason it's called a unit circle is because it has a radius of 1. Well, vectors that have a magnitude of 1, again, magnitude is the same thing as length, those are called unit vectors, and there are two special unit vectors. Again, a vector that has a length of 1, and it is the horizontal unit vector and the vertical unit vector. And they use the letters I and J. Do not confuse this I with the imaginary number I. But they do use these, and not knowing which courses you guys are going to take after pre-cal, I at least wanted to introduce it briefly, and I think there's 1, possibly 2 homework questions that I did include that use the letters I and J. And again, hang tight, the next slide I'll explain what in the world this is. Again, these are the standard unit vectors I and J, the horizontal and vertical vectors that have a length / magnitude of 1. All right, so on this slide, I just tried to write out an explanation of the other notation for vectors. So this says sometimes vectors are written as a linear combination of their horizontal and vertical components using the unit vectors I and J. So just for example, if you have the vector 4, -3 with our alligator brackets, that vector can also be expressed as 4i minus 3j. Typically what I tell my kids, if they see a vector written in this form with i's and j's, they just immediately rewrite it in our component form with our alligator brackets, because that seems to work better for most of my students. So again, don't freak out when you see the i's and the j's. It's just a different way to write the vector. All right, moving on. All right, so it says a precise way to state the direction of a vector is the directional angle, theta, that the vector v makes with the positive x-axis. So easiest thing to do is think about standard position like we did with our unit circle. We would find the measure of the angle and it's done the same way. So if we rotate counterclockwise, as in this picture, remember those angles are positive. If we were to rotate clockwise, then those angle measures would be negative. So hopefully that goes along pretty easily with what we did in the previous units. Okay, I'm going to move on to the next slide. So it says, how can we find the direction angle of a vector? So going back and using that same vector that we started with, the vector u, which was negative 1, 3. So if I can draw that vector in again. So to the left 1 and up 3, and that will be my terminal point. And again, we're trying to find the measure of this angle here. But like we talked about in chapter 4, we can use reference triangles to help us find the measure of that angle. So if I, as we always did before, drop down to the x-axis, that forms a right triangle. Notice the x value here, because we went left, would be negative 1. Sorry, it was so small, so I had to kind of jot that down there. And then the y coordinate would be a positive 3. And again, we're going to, I don't have much room here, but we're looking really for this little angle in here. Like, what would the measure of that angle be? And if you notice, you have the side that is opposite and you have the side that is adjacent. And so if you guys remember good old SOHCAHTOA, that would be tangent. And we're trying to find the measure of an angle, which means we would use inverse tan. So if I take the inverse tan of the opposite, which is 3, over the adjacent, which is negative 1, and we'll just do this in degree measure. I won't torture you with radians today. So if you guys can grab a calculator, go in Desmos, and find the measure of this angle for me. So again, make sure your calculator is in degree mode. And when I typed mine in, and I'm just rounding to the nearest tenth is fine. We'll keep it easy today. My calculator told me negative 71.6. And that was in degrees. But if we think about that vector, we can see that that vector lies, its terminal point is in quadrant 2. But negative 71.6 is not an angle in quadrant 2. That is an angle in quadrant 4. Remember, quadrant 4 and quadrant 2 are diagonal from each other. So to get from quadrant 4 to quadrant 2, like we've done in the past, I would need to add, hopefully you all just said 180. So again, this can't just be pure plug and chug. You've got to use your brain a little bit and think about it. So when I add that, the actual directional angle is 108.4 degrees. So pretty simple. Using inverse tan, like in prior units, but paying attention to the quadrant and making sure that your angle matches the quadrant of the terminal point of the vector. And if not, you might need to add 180 degrees. All right, moving on to the next slide. So at the top, I drew a picture of just our basic triangle. Started out with vector PQ, and then I drew in the horizontal and vertical components with the X and the Y. I drew in theta there, Again, a reminder that theta is the directional angle, so rotating from that positive x-axis. And then since vector PQ, since it's a vector, it has length / magnitude, so that's why that hypotenuse, yes, this is a right triangle, that hypotenuse is labeled mag for magnitude. And so a little bit of review, our good old SOHCAHTOA, we just used tangent in the previous slide. So review SOHCAHTOA, cosine is adjacent over hypotenuse, so that would be x over the magnitude. And the sine of theta is the opposite over the hypotenuse, so that would be y divided by the magnitude. So if we want to find the component form when given the direction and the magnitude of an angle, this is really awesome. You think about those two equations I have written in red at the top. If you solve the one on the left for x, you would multiply both sides by magnitude, and that would give us our horizontal component here. So it is the magnitude times the cosine of the angle, so coming from this. And then for the second one, to get the y by itself, you would multiply both sides by magnitude again, and that would give you your vertical component, or y, which is the magnitude times the sine of the angle. So definitely jot those down. That will make your life a whole lot easier. As far as memorizing those, just from our unit circle, your x was your cosine, your y was your sine, so hopefully that is not too big of a jump. All right, I'm going to jump to the next slide. So this one says find the components of the vector v with a direction angle 115 degrees and magnitude 6. So literally you're just going to plug into that equation on the previous slide. So we said that's going to be the magnitude, which is 6, times the cosine of the angle, comma, the magnitude times the sine of the angle. And you guys know that I'm not big on plugging things into a calculator because this is an exact answer. Again, feel free to do that. When you're plugging these in, you will have to make sure you're in degree mode. But one thing that you can think through before you even plug it into your calculator, again, just to check yourself, think about 115 degrees. On my unit circle, 115 degrees would be in quadrant 2. So I know that if I plug this into my calculator, the cosine of 115 is going to be a negative number, and the sine of 115 is going to be a positive number. So again, feel free to type it in, but I know that this is going to be a vector whose horizontal component will be negative and the vertical component will be positive, just based on the directional angle of the vector. All right, moving on. So it's been a long time, but I think earlier in the year, I briefly talked to you guys about bearing. So in navigation, the course or the bearing is the angle that the line of travel makes with due north measured clockwise. So I think we kind of sketched these way back when we were looking at, I believe it was a boat problem. But everything that we have done has been using directional angles. We know that the cosine is the x, the sine is the y, but the angle has always been a directional angle, not course or bearing. So instead of you teaching you completely new formulas that are going to contradict everything that we've worked on, what I'm going to do is anytime that it gives us a course or a bearing, we're going to convert that angle to a directional angle, and then we can just keep using what we've been using all along instead of introducing new equations. So, for example, it says the airplane is flying on a compass heading or bearing, kind of use those two words interchangeably, of 170 degrees at 460 miles per hour. A wind is blowing with the bearing of 200 degrees at 80 miles per hour. So I split this question up into 3 parts. You'll see a question or two like this in your homework, and they do not split it up into these pieces. I think it makes it much easier. So even though those questions don't have an A, B, and C, as you work through them, I would encourage you to make a part A, part B, and part C. So we just need to find the component form for the velocity vector of the airplane, the velocity vector for the wind, and then to find the actual ground speed and direction of the plane, then we will combine those two forces together. As you know, depend upon if the wind is blowing with you, behind you, or against you, will change your flight time. I don't know if you guys have flown, like if you fly to California and you fly back, the time is not going to be, the flight time is not going to be the same due to the wind. But as I mentioned, we don't want to have to come up with new equations. So the first thing we're going to need to do is convert these headings to direction. So I'm going to start off with the first one and doing a little sketch here. It says a heading of 170 degrees. So 170 degrees would have been this angle, something like that. But I want the directional angle. So the direction, remember, is measured from the positive x-axis. And again, I could rotate all the way around, but I would like to use smaller angles if I can. So we know that there's 180 degrees in a line. And so the purple angle did all but those 10 degrees. And we know that there's 90 degrees in a quadrant. So that would be negative 80 degrees. Or if negative angles freak you out, feel free. You can change that to a positive 280 degrees. To me, I could do it in my head a little bit easier just thinking of the negative 80, but that's totally up to you. So if I want to write the component form of the velocity of the airplane, then I can take the magnitude, and the magnitude in this case is the speed or the velocity of the airplane. So that would be 460 cosine, and I'm going to put a parentheses in here, negative 80 degrees, comma, 460 sine of negative 80 degrees. Again, using my alligator brackets to remind me that that is the component form of the vector. So I can see that horizontal and vertical components. All right, we're going to do the same thing now with the wind. Again, I'm going to draw a picture. The wind was blowing with a bearing of 200 degrees. So again, bearing is measured from due north. So 200, that would be 180 plus, that would be another 20 degrees. So that is a 200 degree bearing. But if I want to convert that to direction, I have to find this angle. And we know a quadrant is 90, and we had said that extra little piece there was 20. So 90 plus 20 would give me 110. But again, since I am rotating clockwise, that would be a negative 110 degrees. So my component form for the wind would be the magnitude, which is the velocity, so 80 cosine of negative 110, comma, 80 sine of negative 110. So now it's time to find the actual ground speed and direction. So what we're going to do here is we have two forces that are acting on the plane. We have the actual plane itself and the pilot, and then that's making the airplane go, and then we have the wind. So to find the actual ground speed, we're going to add parts A and B. And I'll let you guys do that in your calculator or Desmos, whichever calculator you're using. So again, we would add the two horizontal components together, so the x's, and then add the two vertical components together, the y's. So I'll give you a second to type those in. And again, that's going to give me my alligator brackets. So if we take our 460 cosine negative 80, our 80 cosine negative 110, and we add those together, if I did this correctly, that will give me 52.5. And then I'm going to do the same thing with the vertical components. Add the vertical component of the airplane plus the vertical component of the wind. And again, if I type that incorrectly, that gives me negative 528.2. So those are the actual horizontal and vertical components of where the plane is actually going. So again, remember, the first coordinate is your x or your horizontal. The second coordinate is the y or the vertical component. And so our magnitude, remember that was where we used the Pythagorean Theorem. So it was just the square root of x squared plus y squared. And then we can go ahead and plug that in, and that will give me the actual speed of the plane. And by the way, if you get a negative speed, you should realize you did something wrong. All right, so I came up with 530.8 miles per hour. Hopefully you did as well. All right, and the other thing we need to find is the direction of the plane. And since it says direction, I'm just going to find the direction angle. I'm not sure if the back of the book does direction or bearing. I think the North Carolina final exam does like east and west and north and south and using angle measures. But as you guys have probably heard, there will not be any NCFEs this year. So I'll just teach you this one way, and then you can apply that in future math courses. So like we did in an earlier slide, to find the direction, so to find theta, we take the inverse tan of y over x. And when I plug that into my calculator, I got negative 84.3 degrees. Oh, but I forgot to check. Is that actually the right answer, or do I need to add 180 degrees like the last time? Well, to answer that question, let's look back here at our component form. So we had our x was positive and our y is negative. So that vector would be in quadrant 4. So therefore, that angle is correct. I do not need to add 180 degrees this time because the angle measure, negative 84.3, would put me in quadrant 4. So that is an application problem of how you can use the component forms of vectors to combine two forces to find the actual magnitude, in this case speed, and direction that the plane was flying. All right, at this time we're going to move on to section 6.2, which is dot product of vectors. This is a really short and easy lesson. At least I think so. I think you will too. There's kind of a weird formula in here for one piece, but most of it is really easy. So 6.2 dot product of vectors, found in your textbook on pages 514 through 17. Again, I have shortened what I would normally be teaching in the classroom and just kind of going over the most important pieces with you today. All right, so a dot product, also known as an inner product. You'll hear me call it a dot product, but some textbooks and teachers will call it inner product. So if we have two vectors, u and v, Again, notice these are, we know they're vectors because of the alligator brackets. So we have those horizontal and vertical components for each one, labeled U1, U2, and V1, V2. And the way you find a dot product is you multiply the horizontal components and you multiply the vertical components, and then you add them together. So really easy. You may have wondered why in the last lesson we talked about adding and subtracting, but we did not do multiplication. Again, this is not exactly multiplication. Again, it's defined as a dot product, and it is not going to give us a vector, and I'm going to talk about that in a future slide. So definitely write down this formula. We'll be using this throughout the rest of today's lesson. So horizontal components, their product, plus the product of the vertical components. All right, so we can use the dot product to find the angle between two vectors. So that's one of the major things that a dot product is used for. Some observations. The dot product gives us a scalar. By the way, a scalar is just a number, so it's not a vector. So like we added them, we added vectors in the previous lesson, we subtracted vectors, but a dot product does not give us a vector. It just gives us a number. And it says the dot product is similar, but not the same as multiplication. Multiplication is involved in how to find a dot product, but it is not the same as multiplication. We do not go over vector multiplication. It's just called the dot product. So again, this slide is just some observations, nothing major here. All right, moving on. All right, so we're just going to do 3 quick little examples. And if you glance over these, if you'll notice, I stuck in letter C with the I's and the J's, just as a quick reminder. So to find each dot product, it says that we multiply our horizontal components. And again, this is not a vector, so I'm not using alligator brackets. So I'm going to do 3 times 5 plus, and then we're going to do the vertical components, and that's 4 times 2. So 15 plus 8 is 23. And that's all a dot product is. It just gives us a number. Again, a scalar. So horizontal times horizontal plus vertical times vertical. The second one has some negative numbers in there. Be careful, some of you struggle. So we have 1 times negative 4 plus negative 2 times 3. So that will give us a negative 4 minus 6, or negative 10. All right, so for letter C, again, don't panic when you see the I's and J's. Again, just go ahead and rewrite it in the alligator bracket component form that you're accustomed to. So for the first vector, that's just going to be just 2 comma negative 1 dot product, and the second vector would be 3 comma negative 5. And so now we're ready to multiply. We're going to have 2 times 3 plus negative 1 times negative 5, which would be 6, and then that's a negative times a negative, so it turns it into a positive, and that dot product is 11. So it's super easy. I think that I have seen this maybe on the most recent North Carolina final exam. I think in the prior ones they had not included dot products. But I think with the new standards for next year, you guys won't be taking pre-cal, but I think dot products is definitely going to be part of our new standards. All right, going to move on to the next slide. So this is what I was talking about, this kind of the crazy formula. It looks kind of scary, but as I mentioned earlier, a dot product can be used to find the angle between two vectors. So to find that angle theta, we use our inverse trig function, and we use inverse cosine. Remember, cosine, our restricted range for cosine, inverse cosine, is from 0 to 180, so quadrants 1 and 2. And so when we find an angle between two vectors, it has to be between 0 and 180. So the numerator here is the dot product of the two vectors. And then if you remember me mentioning earlier, those absolute value bars, that is giving you the magnitude. So we're doing the magnitude. So sometimes I will have my kids say this out in words, then instead of trying to memorize U's and V's and dots and absolute values. I think that gets a little crazy. For those of you that don't like to just take it at my word, and I totally get that, there is a proof using the law of cosines on pages 515 and 16 in your textbook if you're interested. But the way that I go through this, and I'm going to write it down here at the bottom, is I said you take the inverse cosine of the dot product divided by the product of the magnitudes. Might be a little confusing there because I used the word product twice, but notice the first time it's the word dot product, the second time it is just product. So the inverse cosine of the dot product divided by the product of the magnitudes. And I just have to say that to myself several times to kind of get it to stick. All right, so let's give this a shot. Okay, so here we have two practice problems for finding the angle between the vectors u and v. I'll work the first one for you, and then I'll give you guys a couple minutes to work through part B. So I'm going to use the phrase that I had written at the bottom of the previous slide that says to find the angle between the vectors, we take the inverse cosine of the product, the dot product. So again, I'm going to take horizontal times horizontal. So 2 times negative 2 would give me negative 4, plus vertical times vertical. So 3 times 5 would give me 15, over. And then remember that the denominator is the magnitude of the two vectors. And the magnitude, again, that's where we use the Pythagorean Theorem. So if I take vector u, the square root of x squared plus y squared, that's going to give me 4 and 9, which would be the square root of 13. And then we are multiplying that by the magnitude of vector v. So again, Pythagorean theorem, the square root of x squared plus y squared, which would be 4 plus 25, so the square root of 29. And now literally can just type that into my calculator. Be careful, you might want to at least simplify the numerator as you're typing that in, or make sure you're using parentheses. So inverse cosine of, I guess that would give me 11 on the top, and then the bottom, the square root of 13 times the square root of 29. And if I plug that in correctly, I come up with 55.49 degrees as the angle between these two vectors. All right, take about a minute and try part B. Okay, I'm going to start working through this. If you're not ready, feel free to press pause. So to find theta, the angle between the two vectors, I do the inverse cosine of the dot product. So that would give me -2 plus -3 over the magnitude of the first vector. So I would do 2 squared plus 1 squared, which would be the square root of 5. And then for the second vector, I would get 1 plus 9, which would be the square root of 10. And if I plug that into my calculator, that gives me a nice answer this time, 135 degrees. And you might wonder why that's the case. So think about if we simplified this, -3 and -2 would give me -5. And on the bottom, I would get the square root of 50. And if we go through and do some rationalizing and simplifying, we will end up with, if you remember, the cosine of 135 is -√2 over 2. I'm not going to go through all that simplifying here because you guys are probably a little tired by this point, as am I. All right, one last note about dot products before we finish up. Vectors are called orthogonal if their dot product equals 0. Sounds like a fancy word, but orthogonal is just another word for perpendicular. So when vectors are perpendicular, they are said to be orthogonal. So again, anytime you do a dot product and the dot product is 0, you would immediately know that the angle between them is 90 degrees because they are perpendicular. So kind of a nice little shortcut. I can't remember if any of the homework problems turn out to be an angle between the two vectors is 9 degrees, but I think there's at least a couple questions that ask you if the two vectors are orthogonal or not. All right, you guys have been champs. Thank you so much for working with me. Your quote homework, number 1, you need to take the Unit 14 post-test and grad point. Again, feel free to work through the lessons and the quizzes to help you review. Also know that you've got your old study guide on Canvas, which hopefully you worked on over the last month. And then these are not the assignments you'll find on the assignment page. It's kind of null and void now that we are in remote learning. But these are some practice problems from section 6.1 and 6.2. It's not everything that I originally had planned, and I don't think it's too terribly many practice problems, and a lot of these, again, are pretty quick, especially with the dot product. So those 2 sections, and then number 4, just please make sure you've checked PowerSchool for any missing work from quarter 3, and I've put notes in there for quite a few of you that have missing quizzes and tests, but just email me for instructions on what you need to do to get those made up. Hope you guys have a great week. Again, please don't hesitate to reach out to me if you need any help. There's my email address. And again, you can also message me through Canvas. Hope everybody's doing well. I miss you guys, and I will talk to you soon. Also, if you guys want to give me some feedback as far as going over the homework, I thought about hosting maybe a Google Meet, or if you guys just email me questions, I can also work those out and post those on Canvas. So just let me know what you prefer. Take care. Bye.